You'll be able to see that programme again on Thursday morning at 6:30 here on 2. And next week's edition of the Maths Foundation course is part of the modelling block, which looks at how mathematics is applied to problems in the real world. The reason why cranes don't fall over is because engineers have applied the principles of mechanics to them. These principles are based on a mathematical analysis of the forces involved, which starts by simplifying the structure of a model to its bare essentials. And you can see that analysis next Sunday at the regular time of 9:45. But our concern now is with homeomorphisms, geometric objects which are topologically equivalent. This is a program for the second level course, An Introduction to Pure Mathematics.
Well, this is a program about topology. Perhaps you know something about topology already. Perhaps you've read a popular mathematics book and you've seen that topology is about the kind of transformation that we've just seen happen to this watch. Well, certainly that was a topological transformation. But thinking of topology just as interesting transformations like this is perhaps a little misleading. What we're going to try and show you in this program is that topology is a basic subject, one which underlies a lot of mathematics. In fact, there's a theorem that we proved earlier in the course, which is really a topological theorem. It's the intermediate value property. If you have any continuous function defined on an interval, then the function takes all values between the images of the endpoints of the interval. In particular, if the images of the endpoints are above and below 0, then the function takes the value 0. That is, the graph must cut the x-axis. And this is true if we replace the graph by any continuous curve. The curve must cross the axis. Well, that's a theorem that I hope you know very well. But why do I say it's a topological theorem? Well, the reason is because of the way we've set the theorem up. You see, the way we've set it up, it says if you've got any curve in the plane, and if the endpoints are on either side of the axis, like that, then the curve has to cross the x-axis somewhere. And you see, it's a very clear property, because the x-axis divides the plane into two regions. And there's no way that you can get from this region to that region by a continuous path without crossing the axis. It's very clear, it's very obvious. The x-axis breaks the space into two pieces. So the intermediate value property from this point of view is extremely clear, but why does it have to have such a difficult proof? Well, the reason is because the consequences for the real numbers are so important. Suppose we look at the intermediate value property again, but this time we let our curve be the graph of y equals x to the 57 minus 2. Now, because this theorem tells us that this curve must cross the x-axis, it also tells us that the equation x to the 57th minus 2 has a root, namely the 57th root of 2. And the same thing happens for any root of any number. And now I think you can see why the intermediate value property has to use completeness. Because completeness says that the number line, like this x-axis, is complete. It has no gaps in it. For instance, if there were a gap in it, say the 57th root of 2 wasn't there, then this path could slip across the axis, passing through that gap, and not intersect it. Well, this idea of being able to join points by a path lying entirely in the space, or not being able to join points by a path lying entirely in the space, that's a topological idea. Well, in order to make it precise, we're going to need a definition of topology.
Topology is a geometry, and in order to show you what we mean by that, and to show you how it fits into the Kleinian hierarchy of geometries we met earlier in the course, I'm going to start quickly with Euclidean geometry. In Euclidean geometry, we can move figures around in space. A figure like this, for instance, a triangle, the line through one vertex bisecting the opposite side. And we can move it around in such a way as to keep the size and the shape the same. We're not allowed to change those, and so angles and length are properties in Euclidean geometry because they're kept invariant by the group of transformations for that geometry, the rigid body motions in space. Those are the Euclidean transformations. The next geometry in the hierarchy was similarity geometry. Now we can still move the figures around, but we can expand them, or as in this case, shrink it down. And so we say that angles are still a property of the geometry because they're left invariant even by the new transformations, but length is not a property because we can change it by a transformation appropriate to similarity geometry. Okay, that's similarities. The next geometry was affine geometry. Now we lose angles. We can transform our triangles so these angles aren't the same anymore, but the lengths along the lines still have the same ratio. Ratio along a line is preserved under affine geometry, and so that's an affine property. The last geometry we met in the course so far was projective geometry. A projective transformation could turn our triangle into this. Not only have the angles gone, but ratio along a line has gone. Yet it's still recognizably a triangle. And projective geometry stood at the top of the hierarchy. So where does topology fit in? Well, now our triangle has rather sadly undergone a topological transformation, and not very much seems to be preserved. I think you can still see, though, that there's this line, and the triangle has become the dark closed curve here. But what kind of a transformation is this, and why do we say that it generalizes the ones we've met before? Well, at least it's a continuous transformation. I mean that nearby points, sufficiently nearby points in the original figure, remain nearby in the transformed figure. And I think you can also see that there's an inverse to this transformation. We could get hold of the triangle and pull it back into shape. And that transformation would also have to be continuous. It is in the given case, but it would have to be because we want the transformations to form a group. We want the group of all continuous transformations of our triangle. And it's worth thinking for a moment about what the group of all continuous transformations of some space or other would have to look like. If we have a continuous map from a space onto itself, and we want these continuous transformations to have inverses so that the collection of all of them form a group, then the inverse must certainly exist. So that map becomes not only onto, but also one-to-one. And the inverse is also continuous. So these are the transformations in our new geometry. They are continuous transformations with continuous inverses. Such transformations are called homeomorphisms. Notice the E in homeomorphism. And for any space, we have a group now of all homeomorphisms of that space. That's our group, and it's in that sense that we have a geometry, the group of all homeomorphisms of the space. And because we have a group, we can talk about invariants, things left invariant by the group. And those things would be geometrical properties for that geometry. The geometry is called topology. The invariants are called topological invariants. And of course, you want to know what kind of things topological invariants could be. And that rather depends on your intuition about homeomorphisms. For instance, if you think that this triangle, this homeomorphism of a triangle, is a wild thing to do to a triangle, we're going to show you that actually it's a pretty tame transformation.
Well, now you've seen a few examples of homeomorphisms, and I expect you can use your intuition to fill in some more examples. But let's look now at the opposite problem, the problem of proving that things are not homeomorphic. For example, here are two very simple spaces. This is an interval of real numbers, and this is a circle in the plane. And they're obviously not homeomorphic because if I have a homeomorphism taking the interval onto a circle, the two endpoints are going to come together, then the inverse transformation will tear them apart again, so it won't be continuous. But what we need is a proof that they're not homeomorphic. And we're going to construct a proof which is essentially going to use the idea that we met earlier, the idea of connectedness of a space being all in one piece. Well, at first sight, the idea doesn't help us at all because both these spaces are obviously in one piece. But there's a trick. What we're going to do is to remove a point from the middle of that space. And then if we have a homeomorphism, we can remove a point, a corresponding point, from the circle. And now we're going to have a homeomorphism between these deleted spaces, the spaces with the points missing. This one's in two pieces, and that one's in one piece, and we'll get a contradiction. Well, now, I'm going to give you a proof based on this idea, but using the intermediate value property. Then after you've seen the proof, I'll explain how this idea of connectedness fits in. So assume there is a homeomorphism f from the interval to the circle. Remove a point from the interval and its image from the circle. The restricted map remains a homeomorphism. We'll now mark the images of the endpoints of the interval on the circle. Now there's a path in the circle between those images which avoids the point we've removed. Composing with the inverse of f, we get a path in the interval which also misses the point removed. But that contradicts the intermediate value property. Any continuous path between the endpoints must cross all points in between. So there can be no homeomorphism. So here's how the proof goes. You've got a homeomorphism between the interval and the circle. You remove a point from the interval. You remove the image point from the circle. You consider the images of the endpoints in the circle. There's a path in the circle joining them. You carry the path back by f inverse. You find a path in the interval joining the endpoints, but missing the deleted point. And that's not possible because the intermediate value property says whenever you've got a continuous function from an interval to an interval, then it takes every value between the values taken by the endpoints. And this path takes these two values as endpoints, and it's not supposed to take this value. So that's a contradiction. But how can we phrase that topologically in terms of a topological invariant? Well, let's say that a space is path connected if whenever you have 2 points in it, like these 2 points, then there's a path joining them lying entirely in the space. So the deleted circle, the circle minus this point, is path connected. Whereas the deleted interval, the interval minus this point, is not path connected because there's no path lying entirely in the space, starting at this point and ending at that point. And path connectedness is a topological invariant because if you have any homeomorphism, it carries a path in one space over to a path in the other space. So now we can summarize the proof using this topological idea very quickly. If there's a homeomorphism between the interval and the circle, there's a homeomorphism between the deleted interval and the deleted circle. Deleted circle is path connected, deleted interval isn't. Contradiction. Well, as a matter of fact, there's another invariant we could have used, perhaps a more obvious one if you look at it. You see, every loop, every closed path coming back to itself in the interval, is in some sense inessential. It can be shrunk down to a point. But that's not true in the circle, because if you consider the loop that goes once around the circle, there's no way of shrinking it. We'll say that a space is simply connected if every closed path, every loop, can be shrunk down to a point. So this space is simply connected, but that one isn't. So they can't be homeomorphic. Well, we haven't proved that simple connectivity is an invariant, but nevertheless, let's assume that it is, and go ahead and use it to distinguish some more spaces topologically.
The spaces we're going to try and distinguish are these three, which I have here, And the invariant, the topological invariant we'll use will be simple connectivity, as Colin said. So first of all, what are the spaces? Well, this one is a disk, a planar region bounded by a circle. The second space is the sphere, and I'm thinking of it as hollow. It's just the surface of the ball. That's the topologist's sphere. And the third one, this ring-shaped object, which might to some of you resemble a donut, is known to topologists as a torus. Again, I think of it as round, hollow, just the surface you can see in the ring. So these are my three spaces, and the invariant simple connectivity is going to be put to work. Now, I'm going to try it first of all on these two spaces. Remember, simple connectivity means that any closed path in the space can be continuously deformed down to a point. And I claim that the sphere, in fact, is such a space. The sphere is simply connected. We have to show that any curve in it whatsoever can be continuously shrunk down to a point. So let this stand for a typical curve, although to a topologist a typical curve might be much more ornate and overlap itself several times. To show that it can be contracted down to a point, you just push it, first of all, off the North Pole, and then standing on the North Pole, sweep downwards towards the South Pole, sweeping the curve before you as you go, and finally contracting it to a point at the South Pole. So the sphere is simply connected. So is the disk. It's easy to see that the disk is simply connected. You just pick your favorite point in the disk, and then, given any closed path in it, suck that path in to your favorite point. This contracts the path down to the point. So the disk is simply connected as well. Well, okay, if both of these spaces are simply connected, how on earth can we use simple connectivity to tell them apart? Well, we do exactly what Colin did before with his problem. We use the same trick of removing a point from the spaces. To be precise about it, let's suppose, for a contradiction, that the disk and the sphere are simply connected, and we have a homeomorphism from the disk to the sphere. Well, then we remove a point from each space. Remove a point from the interior of the disk, and its image under the homeomorphism from the sphere. The homeomorphism restricts to a homeomorphism of the punctured spaces, the disk minus the point, and the sphere minus the point. But the sphere minus the point is still simply connected. You just stand now at the puncture and sweep everything before you as you go, collecting the curve down, any curve at all, down to the antipodal point. The punctured sphere is still simply connected. But the punctured disk is not. That's easy to see. For example, this curve going round the point cannot be contracted down to a point. The puncture gets in the way. The only place you could contract it to would be the puncture, and the puncture isn't part of the space. So the punctured disk is not simply connected. Yet simple connectivity is, we have said, a topological invariant. And we started off by saying we had a homeomorphism from disk to sphere. This gave us a homeomorphism from punctured disk to punctured sphere, but this space is not simply connected, although this one is. Contradiction. So if the punctured spaces aren't homeomorphic, neither are the spaces themselves. Very well, that's the disk and the sphere. They're topologically distinct. What about the torus? Well, simple connectivity works like a charm when applied to the torus because the torus itself is not simply connected. For example, this curve going once around the torus like this cannot be contracted down to a point. Remember, we carefully said the torus is hollow, so you can't contract this curve inwards. You have to stay on the surface. And if you do stay on the surface, no amount of pulling and squeezing will deform this curve down to a point. It's wrapped around the torus, it stays as a curve. So the torus is not simply connected, and that distinguishes it from either the sphere or the disk, which were. So I now have three spaces which are topologically distinct, and I can go on and make more. I can make them in the way that a topologist will make a sphere into a torus by attaching a handle. If I take a tube like this, again hollow, and attach it to the sphere, so I have now a sphere with a handle. If I squeeze the sphere down so it's no wider than the handle is, I have a torus. I can just deform this shape into a torus-like shape, and that's continuous. Very well, a sphere with one handle is a torus. So I'll make a new space by taking a handle and attaching it now to a torus. there's a new space, a torus with one handle. I can add handles. Each time I add handles, I get a new space. I'm not going to prove that very rigorously. There's a proof in the unit. It's another counting invariant. And if I go on adding handles in this fashion, I get more and more spaces. So I have here now a torus with 1, 2, 3 handles, and that's a new space. And I can go on adding an infinity of handles and getting new spaces each time. And so I have, in fact, an infinite family of topologically distinct surfaces.
So, in this program, we've defined topology. Topology is the geometry, which the group is the group of homeomorphisms in the Kleinian sense. So, topological invariants are properties of spaces that are preserved by homeomorphisms. And we gave you 2 examples of topological invariants. The first one was path connectedness. A space is said to be path connected if whenever you have 2 points in it, there's a path lying entirely in the space. And the second invariant was simple connectedness. A space is said to be simply connected if whenever you have a closed path, you can shrink it down to nothing entirely within the space. And we use those topological invariants to tell some spaces apart. And this gives you some idea of what topology is like. You see, we started with something which was inherently floppy, the geometry in which things droop. And we've ended up with some very precise, sharp invariants. Typically, topological invariants count things like the number of pieces a space is in, or the number of non-trivial loops in a space. Well, that's the introduction to topology. In the next program, we're going to look at an interesting kind of topological construction, a knot.
In next week's programme for this introduction course in pure mathematics, Colin Rourke and Alan Salmon will be introducing viewers to the branch of mathematics known as knot theory. And you can find out what the knot theory is at 10 next Sunday here on 2. Our next programme in a couple of minutes continues the topic of geometric topology, this time for the 3rd level course, Studies in Pure Mathematics. Studying with the Open University is for many people a stimulating, challenging and deeply rewarding experience. The Open University is genuinely open to any adult who wants university-level education. Entrants are selected on a first-come, first-served basis, and no previous qualifications are required. The university's teaching methods are different from those of other universities because they're designed for people who want to study in their own time, at home, without giving up their jobs or domestic responsibilities. Its degrees, however, are recognized as equal to those of any other university. Since the university began teaching in 1971, over 60,000 students have graduated with BA degrees. A majority of them say that their careers have benefited. For some, it's meant promotion, some a change of occupation, and others an enhanced performance in their existing jobs. This year, more than 100,000 men and women will be studying Open University courses. And next year, you could be among them, working towards a BA degree, advancing your knowledge to advance your career, or studying for the sake of studying. Next year, you could get that second chance you've always wanted. So why not take the first step towards becoming an Open University student and write to this address? It's the admissions office, the Open University, P.O. Box 48, Milton Keynes, MK7 6AB. You'll be sent